Welcome back to G-Fun Facts Online. Today we are diving straight into what is arguably the most profound and fiercely debated crisis in modern astrophysics. For over a century, humanity's understanding of the cosmos has been governed by one undeniable truth: the universe is expanding. But the exact speed at which it is expanding, a specific number known as the Hubble constant, has completely broken our models of the universe. We have two incredibly precise sets of measurements. They use completely different methods, and they give us two completely different answers. This is known as the Hubble Tension. It suggests a terrifying and thrilling reality. Either our most sophisticated, multi-billion-dollar cosmological measurements contain hidden flaws, or our fundamental understanding of physics and the universe is missing a crucial piece of the puzzle. For years, astrophysicists have scoured the cosmos for an independent arbiter to settle this dispute. We needed a tiebreaker. And now, a revolutionary technique using the faint, cumulative hum of billions of colliding black holes, a phenomenon newly dubbed Stochastic Sirens, promises to break the deadlock. We are learning to measure the expansion of the universe not by looking at it, but by listening to it. To truly understand why stochastic sirens are such a monumental breakthrough, we first have to understand the crisis they are meant to solve. The Hubble constant isn't just a random number. It dictates the age, the size, and the ultimate fate of our entire universe. Historically, cosmologists have measured this constant using two primary, largely independent avenues. We call them the early universe method and the late universe method. Let us start with the early universe method. This approach relies on the cosmic microwave background, often referred to as the CMB. The CMB is the residual afterglow of the Big Bang itself. It is the oldest light in the universe. Satellites like Planck and ground-based observatories like the Atacama Cosmology Telescope have meticulously mapped the microscopic temperature fluctuations in this ancient light. By looking at these fluctuations and applying our standard model of cosmology, known as lambda cold dark matter, scientists can mathematically extrapolate exactly how fast the universe should be expanding today. And this method is incredibly consistent. It produces a value of approximately 67.4 kilometers per second per megaparsec, with an incredibly tight margin of error. It is mathematically elegant and precise. But then, we have the late universe method. Instead of looking at ancient light and calculating forward, the late universe method measures the expansion rate locally and directly. Astronomers build what is known as a cosmic distance ladder. They observe objects with known intrinsic brightness. These are usually pulsating stars known as Cepheid variables, and exploding stars known as type Ia supernovae. Because we know exactly how bright these objects actually are, we can compare that to how bright they appear to us through our telescopes. This comparison gives us their exact distance. Then, by analyzing the redshift of their host galaxies, which is how much the light from the galaxy is stretched out as it moves away from us, scientists can calculate the expansion rate. Led by massive collaborations like SH0ES, utilizing the Hubble and James Webb Space Telescopes, the late universe method yields a significantly faster expansion rate of about 73.0 kilometers per second per megaparsec. Initially, scientists were not entirely panicked by this gap. They assumed that as our telescopes improved and our data sets grew larger, the error bars of these two methods would eventually overlap. But the exact opposite happened. As our instruments grew more powerful, the error bars shrank, isolating these two values into distinct, irreconcilable islands. The tension hovered at a statistical significance of 5 sigma. In particle physics and cosmology, 5 sigma is the gold standard for a discovery. It means the odds of this discrepancy being a mere statistical fluke are less than 1 in a million. While some recent local observations of distant supernovae and refined Cepheid measurements have hinted at values slightly closer to 70.4, deeply puzzling anomalies remain. The tension is firmly at the forefront of cosmological research. Are we completely misunderstanding the early universe? Is there a mysterious early dark energy that temporarily accelerated expansion right after the Big Bang and then vanished? Or is there an unseen systematic error in how we calibrate the brightness of stars on the cosmic distance ladder? To answer these questions, science needed a completely independent measurement. We needed a ruler that does not rely on light. This is where Albert Einstein enters the story, over a century ago. In 1916, Einstein predicted that the acceleration of massive objects would actually create physical ripples in the fabric of spacetime itself. He called them gravitational waves. Exactly a century later, the LIGO collaboration announced the first direct detection of these waves, emitted by a pair of colliding black holes. This discovery opened an entirely new sensory window to the universe. For cosmologists, gravitational waves offer something almost magical. They are self-calibrating. When two compact objects, like black holes or neutron stars, spiral inward and merge together, the gravitational waves they emit carry a very distinct signature. By analyzing what physicists call the chirp of the signal, which is how the frequency and amplitude of the waves change over time as the objects spin faster and faster, we can directly determine the absolute distance to the collision. Think about how incredible that is. Unlike measuring the brightness of a star, which can easily be obscured by cosmic dust or flawed assumptions about the star's chemical composition, gravitational waves travel through the universe completely unimpeded. They interact so weakly with matter that their signal arrives at Earth in a pristine, untouched state. This allows gravitational waves to bypass all the fragile rungs of the cosmic distance ladder entirely. This brilliant property earned them the moniker Standard Sirens, a concept first theorized by Bernard Schutz in 1986 and later expanded upon by physicists Daniel Holtz and Scott Hughes. However, there is a catch. To calculate the Hubble constant, knowing the distance alone is not enough. You also need the object's velocity, or its redshift. Because gravitational waves scale uniformly with redshift, the waveform alone cannot easily tell you how fast the host galaxy is receding away from us. You need a way to connect the gravitational wave's pure distance measurement to a specific redshift. The quest to find the redshift of gravitational wave sources has led to a fascinating taxonomy of siren methodologies, each with its own brilliant innovations and frustrating limitations. The most straightforward method is known as the bright siren. If a gravitational wave event is accompanied by a literal flash of light, such as the spectacular collision of two neutron stars observed in 2017, known as event GW 170,817, astronomers can point traditional telescopes at the source. The flash of light provides the redshift, while the gravitational waves provide the exact distance. That 2017 event yielded the very first gravitational wave measurement of the Hubble constant, landing right in the middle at roughly 70 kilometers per second per megaparsec. But there was a problem. The precision of that measurement was only about 30%. That is nowhere near tight enough to resolve the Hubble tension. Furthermore, bright sirens are incredibly rare. Black hole mergers, which make up the vast majority of our gravitational wave detections, emit absolutely no light. They are completely invisible to traditional telescopes. To utilize these invisible collisions of black holes, astronomers had to turn to a method called dark sirens. In this approach, scientists take the localized region of the sky where the gravitational wave originated and cross-reference it with massive three-dimensional catalogs of known galaxies. By treating every single galaxy in that volume as a potential host for the black hole merger, they can use statistical probability to infer the redshift. Over time, by stacking dozens or hundreds of these dark sirens on top of each other, the true value of the Hubble constant begins to emerge from the statistical noise. However, dark sirens face massive hurdles of their own. The universe is incredibly vast, and our galaxy catalogs are severely incomplete. Faint, extremely distant galaxies often go completely unrecorded by our telescopes. While recent studies have shown that clustering, which is the tendency of faint galaxies to group around brighter, catalog galaxies, helps mitigate some of this bias, a remarkably high degree of catalog completeness is still required to prevent the final measurement from being skewed. Scientists have also tried other ingenious methods to break the distance redshift degeneracy without relying on galaxy catalogs at all. For example, love sirens exploit the tidal deformability of neutron stars, utilizing universal equations of state to disentangle the source's mass from its redshift. Spectral sirens rely on known physical limits, such as the theorized upper mass gap of black holes formed from stellar collapse, using these fixed mass scales as standard rulers to infer the redshift directly from the gravitational wave data. Yet, all of these methods rely on one crucial thing: resolving individual, discrete gravitational wave events. And as our detectors become more and more sensitive, the universe is going to reveal a background layer of gravitational waves that are far too distant and far too overlapping to ever be resolved individually. And this leads us to the absolute cutting-edge cosmological tool of the 2020s. Enter the Stochastic Sirens. In early 2026, researchers from the University of Illinois Urbana-Champaign and the University of Chicago, including theoretical physicists Nicholas Yunus and Daniel Holtz, unveiled a completely paradigm-shifting approach. Rather than relying on isolated, loud collisions, the stochastic siren method exploits what is called the stochastic gravitational wave background. To understand this, imagine you are standing at a bustling cocktail party. You might clearly hear the loud laugh of a person standing right next to you. That represents an individual gravitational wave event. But beneath that loud laugh, there is a constant, low-level murmur of thousands of conversations blending together across the entire room. The stochastic gravitational wave background is the cosmic equivalent of that room. It is a cumulative, faint hum produced by millions of unresolved black hole and neutron star mergers, echoing throughout the entire history of the universe. Historically, this background hum was viewed mainly as a holy grail for understanding the overall population of black holes. But Yunus, Holtz, and their collaborators recognized that this background hum encodes a direct, purely gravitational measurement of the universe's expansion history. The absolute brilliance of the stochastic siren lies in the physical relationship between cosmic expansion, spatial volume, and the density of gravitational wave sources. Think about it this way. If the Hubble constant is low, meaning the universe expands relatively slowly, the total cosmic volume over a given time frame is smaller. A smaller volume means that the millions of merging black holes are packed much more densely together. Consequently, the collective gravitational wave background they produce will be noticeably louder. On the other hand, if the Hubble constant is high, meaning we live in a rapidly expanding universe, the cosmic volume stretches drastically. All those millions of black hole mergers are spread out over a much vaster expanse of space. This drastically dilutes the background signal, making the cosmic hum much fainter. By measuring the exact amplitude and characteristics of this background hum, astrophysicists can effectively work backward to deduce the cosmic volume and therefore directly measure the Hubble constant. What makes the stochastic siren method so beautiful is that it actually yields results even before the background hum is definitively measured. In their proof-of-concept tests, utilizing data from the LIGO, Virgo, and KAGRA collaborations, the researchers demonstrated that the mere non-detection of the background at our current instrument sensitivities already provides highly valuable cosmological constraints. Because a very slow expansion rate would produce a background hum loud enough for our current detectors to hear right now, the simple fact that we have not heard it yet allows scientists to definitively rule out extremely low values for the Hubble constant. The stochastic siren effectively sets a strict, mathematically sound lower bound on the expansion rate of the universe. By mathematically integrating this lower bound with the data from individual dark and bright sirens, cosmologists can slice away massive swaths of statistical uncertainty, pushing the accuracy of our measurements to unprecedented levels. The introduction of stochastic sirens represents a crucial turning point in our effort to resolve the Hubble tension for three major reasons. Number one is total freedom from electromagnetic bias. Remember, the late universe methods rely heavily on the incredibly complex astrophysics of stars, like exactly how Cepheids pulsate, or exactly how cosmic dust absorbs supernova light. Stochastic sirens rely solely on the immaculate, pristine physics of general relativity. They are completely immune to the messy, complicated realities of the electromagnetic spectrum. Number two is that there is absolutely no need for galaxy catalogs. Unlike dark sirens, which require meticulous and painstakingly complete three-dimensional maps of the universe to trace host galaxies, stochastic sirens evaluate the volume of the universe holistically. The measurement is completely independent of our ability to see faint galaxies. And number three, it probes the middle universe. The cosmic microwave background measures the universe at a redshift of around 1100, which is just 380,000 years after the Big Bang. Supernovae measure the local universe at a redshift of less than 1. The stochastic background, however, is dominated by black hole mergers occurring at the absolute peak of star formation in the cosmos, roughly at redshifts of 1 to 2. This allows stochastic sirens to act as a crucial bridge, measuring the expansion rate precisely in the middle epoch of cosmic history. This is incredibly important because that middle epoch is exactly where dark energy is believed to have taken control of the universe's expansion. As we push deeper into the late 2020s and prepare for the 2030s, the instruments required to fully unleash the power of standard and stochastic sirens are already taking shape. The current ground-based network, which includes LIGO in the United States, Virgo in Italy, and KAGRA in Japan, is undergoing continuous, massive upgrades. However, the true revolution in cosmology will arrive with the third-generation gravitational wave detectors. Proposed mega-facilities like the Einstein Telescope in Europe and Cosmic Explorer in the United States will boast sensitivities orders of magnitude greater than our current observatories. These third-generation detectors will be so overwhelmingly sensitive that they will capture virtually every single binary black hole merger occurring anywhere in the observable universe. The faint murmur of the stochastic background will be resolved with pristine clarity. Alongside these ground-based behemoths, the space-based LISA Observatory, which stands for Laser Interferometer Space Antenna, will launch into orbit. LISA will capture the slow, low-frequency spirals of supermassive black holes across cosmic time, providing standard sirens that map the expansion history of the universe all the way up to redshift 7. Forecasts indicate that a combined network of next-generation detectors utilizing both standard and stochastic sirens could constrain the Hubble constant to a precision of less than half of 1%. That is tight enough to finally, unequivocally declare whether the early universe or the late universe measurements are correct, or if both of them are actually right and entirely new physics is required to bridge the gap. Furthermore, this multi-messenger symphony will allow scientists to probe the very nature of dark energy itself. By mapping exactly how the expansion rate has changed across different cosmic epochs, stochastic sirens will help determine the dark energy equation of state parameters. This will finally reveal whether the mysterious force driving the universe apart is a static cosmological constant, as Einstein once proposed, or a dynamic, evolving field that changes over time. It may also provide critical tests of modified gravity theories, checking whether Einstein's general relativity breaks down on the grandest scales of the cosmos. The Hubble tension is so much more than just an argument over a number. It is a battle for the soul of modern physics. It forces us to confront the terrifying and thrilling possibility that the universe is far stranger than our best mathematical models suggest. If the tension is a result of new physics, it could mean the existence of undiscovered subatomic particles, exotic invisible fields in the early cosmos, or a fundamental misunderstanding of how gravity operates over billions of light years. For decades, we have tried to solve this profound mystery by peering through lenses and mirrors, capturing ancient photons exhausted by their journey across the infinite void. We have imposed our man-made ladders and our theoretical models onto the sky, but with the advent of gravitational wave astronomy and the brilliant, game-changing innovation of stochastic sirens, we are no longer just looking at the universe. We are listening to it. By tuning into the background hum of colliding black holes, which are the most violent, extreme events in nature, we are allowing the cosmos to speak for itself. Space-time is ringing like a bell, and hidden within its reverberations is the true speed of the expanding universe. As our detectors grow quieter and our algorithms grow sharper, it is only a matter of time before we finally hear the answer. Thank you for listening to this deep dive on Fun Facts Online. Keep wondering, keep listening, and we will see you in the next one.